in hydronium ions. Okay. So for bases, you would treat bases in a similar way to the way we treat acids. If the base is a strong one, then you just use the coefficients in terms of the number of moles of the species that are participating in your reaction. Just make sure that you should know how to differentiate between monobasic or monoprotic acids and polyprotic or polybasic acids in terms of what the expressions are going to be whenever these species undergo ionization. So if you're looking at a simple acid, such as a simple base, such as sodium hydroxide, which is a strong base, it would undergo complete dissociation. So the coefficients that you're going to have would be 1 to 1 in this case, and the concentration of sodium hydroxide would be the same as the concentration of the species that are resulting from the dissociation reaction of this particular species that we have, which is sodium hydroxide. So here it's very straightforward for you to establish what the concentration of hydroxy or hydroxide ions is going to be. For weak bases would be treated in the same manner as we do treat weak acids. We noticed that if I did talk about this in the previous session, or if I did not talk about it, you notice that we have got another constant that we call the Kb. So the Kb constant is the base ionization or base dissociation constant. So when when your base undergoes ionization in solution, notice that nitrogen has got a lone pair of electrons on the ammonia molecule. It can through that pair of electrons, it can interact with water molecules, in which case it's going to abstract protons from the water molecules to form a conjugate acid, which is a protonated ammonium molecule called ammonium ion, and the remaining part from the water molecule, which is the hydroxide ion, is the conjugate base. So you've got your base here, your acid here, as it were. Your water molecules are acting as acid molecules, or your water simply is acting as an acid. When this undergoes protonation, you're going to have the ammonium ion, which is a conjugate acid. Then you've got a conjugate base. So the expression is given in terms of Kb, where you get the concentration of ammonium ions and the concentration of hydroxide ions, and then the concentration of ammonia, which you started off with, in terms of Kb. But this should be very easy to deal with. You simply get the Kb value and the value for the concentration of the ammonia. You multiply the two of them, assuming that the assumption that we'll have made, okay, where you simply that the change is insignificant, you will have to multiply simply the Kb value and the concentration of your base to give you the concentration of hydroxide ions. If you are looking for the concentration of hydroxide ions, it becomes very easy for you to find the concentration of hydroxide ions. All that you need to do is to remember this expression or the equation, and that's all. Okay. For the pH scale, which we would have to use to determine the concentration of hydrogen ions in a given concentration. If anything, pH indicates the presence of hydrogen ions in a given solution, the concentration of hydrogen ions. So it is used to determine the alkalinity and acidity of a solution. And the equation that we're going to have to master would be this very simple equation, where you have the negative log of hydronium ions, or simply the negative log of hydrogen ions. We did introduce you to some aspects when you just started this particular course, your CHE 1000. There was a part that we had introduced to you where we were talking about the significant figures, scientific or standard notations, and whenever you are doing computations, whether be it addition, subtraction, division, or multiplication, there were some things that we had asked you to make sure that you put into consideration, such as determination of what the number of significant figures is supposed to be in the final answer. So make sure that you review all those concepts, because sometimes when we design questions and we come up with marking keys, we may add some emphasis to say if a candidate has not given the answer to these number of significant figures, do not award the mark. It would simply mean that they have forgotten all the concepts that we will have introduced them to. So make sure that from time to time you are going through all those concepts, and they should stick in your minds. If you add the pH itself, you recall that we had told you when this concept of acids and bases and acids, bases, and salts was introduced to you, that pH is considered as a range of numbers where you have numbers starting from 0 to 14 inclusively. That particular scale is demarcated into 2 to 4 regions, okay, into 3 major regions. That is, you have, or rather 1, 2, that is 4 regions. The midpoint between 0 and 14 is 7.0, which is indicative of a pH that is supposed to be considered as being neutral. So any substance whose pH is equal to 7.0 is considered to be a neutral substance. If you have in between 0 and 7, you have 3.5. Any substance whose pH is going to fall within 0 and 3.5 is going to be considered to be a very strong acid. If the pH falls between 3.5 and 7.0, it means the the acid is very weak. If you are going to have a pH ranging between 7.0 and 10.5, the pH of this particular base is weak. If it is between 10.5 and 14, it means the pH, the base that we're dealing with is a strong base. And the closer the number is to 14, the higher the strength of this particular base. And the closer the number is to 0, the stronger the acid is. That is the way we're going to treat pH. So you see those numbers there: 7 equal to 7 neutral, greater than 7, that's basic, and the higher the pH, the more basic. You have less than 7, that is acidic, and the lower the pH, the more acidic a solution is going to be considered. So when we look at some examples, if we gave you the concentration of a substance and we asked you to compute a pH, all that you need to do is to remember this formula here. pH is equal to the negative logarithm of the concentration of that particular acid. So when it comes to getting values of some of the functions that we have on our calculators, such as cosine, sine, and tangent, and logarithms, and what have you, you would have to make sure that your calculator is in the degree mode. Otherwise, when it is in gradients or radians, the values may be slightly different from what you might be expecting. And when marking, we wouldn't know that you came up with the wrong answer because your calculator was in the wrong mode. So it is your responsibility as a student taking that particular test or exam or quiz to make sure that before you even start to answer any questions or read through any of the questions given in the question paper, you put everything in place. Your calculator should be in the correct mode. Yeah, so when you find the negative logarithm of this particular concentration given for this particular acid, you are getting 4.0. A concentration of 0.040 of a base will give you a pH of 12.6, which is closer to what is expected of a base, as it were. But then another aspect that we will have to bring into is you recall that throughout your journey of your learning, at some point you probably might have been introduced to a topic in mathematics called logarithms and exponential functions, especially for those of us that might have done additional mathematics. That is, if that particular concept was introduced to you. So when you're dealing with expressions that might be logarithmic in nature, how do you find the relationship between a logarithmic function and an exponential function? A very simple way of doing it, in this case, this pH equation that you have is given in terms of, it's a logarithmic function. So how do you change it to an exponential function for you to be able to find the concentration of hydrogen ions? You would have to, the logarithm that we're dealing with is given to base 10. So the base is written as a base there, then you raise it to the power negative pH. That is how you change logarithms to exponential functions, a concept that you'll have to review because it might prove to be useful along the way. So the pH value that is given is just thrown into this equation that you will have manipulated, and you'll be able to determine the concentration of hydrogen ions. Okay. The relationship between pH and pOH, you would recall that we had talked about this concept here. You remember the value for Kw? The value for Kw, which we gave as that times 10 to the power negative 14. This is what we had said. So this Kw as at this particular value here. Then this is given in terms of, so the Kw whose value is equal to that is equal to the hydrogen ion concentrations and the hydroxide ion concentrations. So then if, the negative logarithm of Kw, if we were to take the negative, if we introduced logarithms on both sides of the equation to base 10, so we would have the negative logarithm of Kw, the negative logarithm of hydrogen ion concentrations, and the negative logarithm of hydroxide ion concentrations. So the value of Kw is this one here. When we get this value and we bring it here, where pH, pKw, as though we are finding the pH of pK, of Kw, which is this value here, we would get a number. So this negative logarithm of hydrogen ion concentrations is equal to pH. The negative logarithm of hydroxide ion concentrations is equal to pOH. Then the negative logarithm of Kw is equal to pKw. So the value of pKw is known as 14, as being equal to 14.00. So that one is known. So in this particular equation, you remain with two unknowns. Unknowns are the pH and the pOH of any given solution that you might be dealing with. So if you knew one of the two, then you would be able to easily find the value of the other. All that you need to do is to find the difference between pKw, whose value is equal to 14, and what you will have been given in terms of either pH or pOH, as you are going to notice along the way. Along the way when we look at some examples. Okay. So let me just quickly remove this. Calculating the pH of strong acids and bases. So calculating the pH of strong acids and bases is very straightforward. It's not really complicated. All that we need to do is to be able to remember the formulas of acids, and we should be able to know whether the acid that we're dealing with is a mono basic acid, or some of you would refer to these acids as monoprotic acids, or whether you're dealing with the poly basic acids or polyprotic acids. Okay, so if you're able to tell what type of an acid you're dealing with, then it becomes very easy for you to come up with the dissociation equation. So once you're able to establish what the dissociation equation is going to be like, then you'll be able to determine the concentration of hydrogen ions. Such as in this case, we see that, just give me a minute. Give me a minute. Okay, I'm trying to bring up the pointer. Okay. Yeah, so we have
Sir, apologies to stop you, but why are you referring to the acid as polybasic when the acid is acidic? Then another individual also has a question. They have raised their hand for some time.
okay. Yeah. Apologies for that. I am unable to see those hands that are raised because I'm using a phone, so I have to switch between the PowerPoint presentation and the Google Meet software. Sorry for that. So whenever you have a question, you are free to turn on your mic and then you call out to me. Then I will give you a chance to ask your assist your question. So when you are looking at acids and bases, okay. Well, most or maybe some of us probably might not have learned the acid base thought topic fully the way it was supposed to be learned. Uh, those of us that are able to remember, you are able to remember that we dealt with the concept of basicity. Okay, basicity spelled as, okay, let me just write it for everyone to see. So we dealt with this basicity. Okay, so basicity was defined as the number of replaceable hydrogen ions that an acid has. Basicity is defined, do not think of it as being, referring to the concept of something being a base. No. Basicity refers to the number of hydrogen ions that an acid has. Okay, so an acid that has one replaceable hydrogen ion, basicity refers to the number of replaceable hydrogen ions that an acid has. So an acid with one replaceable hydrogen atom is said to be monobasic or monoprotic acid. Let me just write these terminologies for you. So we have, I will give you examples of such acids. So you have who? You have monobasic, or you have monoprotic. Okay, monoprotic acids. So HCl is a very good example of a monoprotic acid. But HCl is not the only example. Even this particular acid, acetic acid. So notice the formula for acetic acid. In acetic acid, only one hydrogen atom is replaceable. These three hydrogen atoms that you're seeing here are not replaceable. They will not be available in solution when this is dissolved in water. So only this one that is connected to the carboxyl group becomes dissociated and is available in solution. So acetic acid as well as HCl are classified as monoprotic acids from the concept of basicity. Basicity refers to the number of replaceable hydrogen ions an acid has. If you look at an acid such as sulfuric acid, let me just write the formula for you. Okay, I'm sorry, we seem to be to have things clustered in the same location, but I'm sure you'll be able to follow. So sulfuric acid has a formula like this one here. Okay, so when you look at sulfuric acid, these two hydrogen ions can become available in solution, can get dissociated from the molecule itself and become available in solution. So it is able to donate two hydrogen ions. Therefore, sulfuric acid is a dibasic acid or a diprotic acid, or if you want, you can call it a polybasic or polyprotic acid, because poly in this case means many and two can mean many depending on how you are looking at it. Is that understood?
Yes, sir.
Okay, good. Okay, so we progress then. So we're saying HCl being a monoprotic acid, it dissociates to only produce one hydrogen ion. And when you look at the coefficients, you've got 1 to 1 coefficients throughout this particular expression. So the concentration of HCl that is given initially becomes equal to the concentration of hydrogen and you get and throw it into the pH equation, you'll be able to determine your pH of this particular acid as being equal to 1, as it were, in this particular example that is species. You have sodium ions and you have hydroxide ions. So when this undergoes dissociation, you will have the concentration of sodium hydroxide given big equal to the concentration of sodium ions as well as the hydroxide ions. So this becomes straightforward. But then notice the way the question is determined. I mean designed. The question says find the POH and pH. So this is for purposes of demonstration. When it comes to questioning you for, in your quiz, when you come to write your quiz and we decide to bring a question like this one, or in your test, we will not give you too much information in a way that might seem like, you being spoon-fed in terms of how questions are being asked. We would simply ask you to determine the pH. But we know that the procedure that you're going to have to use would be first, you determine the POH, then using the POH value, that's when you determine the pH. We know that this being a base, we do not expect to find so many hydrogen ions because pH itself essentially is indicative of the presence in terms of concentration of hydrogen ions. So we're asking you to find the pH, which is the concentration of hydrogen ions in a solution that we expect that it would be dominated by the presence of hydroxide ions. So what do? You're going to find the POH first using the concentration that would have been given for this particular basic solution. So when you find the POH, so you come up with the ionization equation, then you use the coefficients to determine the concentration of hydroxide ions, then you throw that into your POH is equal to minus logarithm of concentration of hydroxide ions. When you find the POH, then you would recall that we had said that the relationship between pH and POH is that 14.00 should be equal to the pH and plus POH. So if the value of pKW is a constant, which is this one here, then you can find the value of the other if one is known. In this case, you know the value of POH. Then you can find the value of pH. Okay, and this is indicative of a solution that is expected to be a base, 12.7, for a very strong base such as sodium hydroxide. If for some reason you forget that you're supposed to use this relationship and you report your pH of a basic solution as being equal to 1.30, the answer would be wrong. Because this is a basic solution, you don't expect the pH to fall in between the pH for that of a strong acid. Recall how we had interpreted the pH scale. We said any solution whose pH is going to fall in between 0 and 3.5 should be regarded as being a very strong acid. And this pH, this value, which is 1.30, is indicative of the pH of a strong acid. So this is a contradiction to what you would expect the pH of a very strong base, which is sodium hydroxide, is supposed to be. So remember all these concepts that we are talking about here and be able to use them correctly. For the second example here, kindly do me a favor. You compute the pH of this is HCl, and we have seen the dissociation equation for HCl. So you do the dissociation equation, you determine the concentration of hydrogen ions, then you throw them into this equation. You'll find that the answer is not going to be 7.0. This was a typo. Kindly correct that for me. Okay, so progress. we move forward. Let me just remove this. To deal with about. We would need to list the major species in the solution. So whenever these dissociation equations are taking place, we are going to have a number of species that might be present in your solution, but we would have to focus on the major ones. Then once we list the major species, then we'll choose the species that can produce hydrogen ions, and we would write balanced equations for the reactions where the production of hydrogen ions is taking place. Then we would need to use the values of the equilibrium constants for the reactions we have written to decide which equilibrium will be dominant in producing hydrogen ions. So what this basically means is that whenever you have a system where a reaction is taking place, you may have a number of species that are participating in that particular type of reaction, all of which or some of which may be responsible for formation of hydrogen ions. Some of them will form hydrogen ions in huge amounts. Others may form hydrogen ions in minute quantities. So the instruction is that you are going to focus on systems that are, for instance, whenever you dissolve an acid in water, water is also going to produce some hydrogen ions. Remember the auto-ionization behavior of water, but we do not consider the contribution from water molecules because it is insignificant. So this is what you are guided to do. Identify systems that are dominant. If we're going to have to focus on one given system, we may not necessarily have to ignore the contribution from other systems. So you see where this is getting to. I insisted on teaching you the previous topic fully to the extent to which we had learned it, because we knew that the concepts that we're going to come thereafter would involve the use of some of the concepts that we had acquired. So if I'm going to design a question at the end of the day for purposes of examining you, I will not create questions where there are segmented concepts. I would put all the concepts together, amalgamate them. The concepts that we acquired in the previous topic and in this particular topic, then generate this very powerful question. Not to scare you, but a question that is befitting, students of the University of Zambia, so that when we train you at the end of the day, we should be confident even ourselves that the people that we have trained are going to be able to handle whatever challenges that they are going to meet in industries or in society. That is the idea. So we can create a question where we tell you in this particular system where this acid was being dissolved, there was already some number of hydrogen ions. So how do you deal with that? Or how do you deal with any other concentrations of species that might be present in there? You remember the concept of reaction quotient. So you would have to determine the reaction quotient, then you determine the direction in which your reaction is going to have to go. Then after you have done that, you come up with the equilibrium concentrations in terms of the value of the change, which is x. Then you come up with the law of mass action. Then you substitute the expression, the concentrations in terms of x at equilibrium. Then you determine the value of x. Then using the value of x, you're going to establish what the concentration of hydrogen ions is going to be. Then you're going to use the formula for pH to be able to determine the pH. So in a very simple way of asking the question, which might sound casual, but the steps that are involved are so many. We will simply tell you in this system we had this concentration of hydrogen ions and this other species was also present with this concentration. Then we got this other substance which might be an acid and dissolved it in there. Determine the pH. It is not a straightforward question, I can assure you. It is a question that would need some very seriousness in terms of some seriousness of some sort in terms of how the question is supposed to be answered. Okay, so you'll have to take all those steps that I've just talked about for you to be able to get to the answer itself. So moving on, you would have to write the equilibrium expression for the dominant equilibrium. Then you list the initial concentrations of the species participating in the dominant equilibrium. Like I said, just in case you might need to determine the value of the reaction quotient for you to be able to establish what direction the reaction is going to have to go into. Because without that, there's nothing that you're doing. Even if you predicted the correct direction, I would put a question mark and say, how did you know? Because I've not seen the value for the reaction quotient, and you have not even told me to say because of the value of the reaction quotient being equal to this compared to the equilibrium constant that have been given, the direction of reaction is equal to, it's going to be this. Then you do not deserve to get marks because it means you're just guessing. And we don't want to train people that are going to be guessing when they go in industries, when you go to work for the mine. Okay, you are employed by one of our mines, and you get into one of the labs that are there, and you do not know what to do. You are guessing. No, we don't guess as chemists. Chemists do not guess. Even if a reaction does not, an experiment does not work out today, I'm going to repeat it the next day, and I'll keep repeating it. If I have to do it forever, I'll keep doing it forever until the experiment works out. That is the way we do things as chemists. We don't guess. Guessing is forbidden. Okay, that is why we are teaching you all these concepts to make sure that we train the kind of students, the kind of learners that should be able to do things correctly. Okay, so the next step would be to define the change needed to achieve equilibrium. That is, define X. When you are able to establish the direction in which the state of chemical equilibrium is going to have to shift into, that is when you bring in this part in terms of the steps that you're going to take. Then you write the equilibrium concentrations in terms of X. When you'll have done that, now you're going to substitute the equilibrium concentrations into the equilibrium expression, which is the law of mass action in terms of the what is either the Ka or the Kb. In this case, particularly, we're dealing with acid-base equilibrium. So, in terms of the acid dissociation constant, then the last two steps that we're going to have to take would be to solve for X the easy way. The easy way would be where we assume that the change that is taking place is insignificant, and we assume the denominator or this part of the equation to only be equal to the concentration that we would have started off with. Then we solve for X. The second last step would be to use the 5% threshold, the concept where you would have to, once you take that assumption, you would have to make sure that the value that you're going to come up with in terms of the change of in terms of the change, the difference between the initial concentration and what the value of X is going to be, compared with what the initial concentration was supposed to be multiplied by 100%, you should get a value in terms of percentage less than or equal to 5%. If it is beyond 5%, you don't need to redo the calculations. All you need to do is to admit to say your assumption was wrong. And when you have to take this assumption, you take this assumption when the value of Ka that is given is small. But sometimes it may not be small enough for that assumption to be warranted. But how do you know then to say your assumption is a warranted one? You have to test. You calculate that percentage. If it is less than 5%, well and good. If it is equal to 5%, it is still okay. But should it be above 5%, then you are going to admit and say the assumption that you made was a wrong one. Then you progress and answer the rest of the question or any other question that you might be required to answer. Then the last step, of course, is where now you find the concentration of hydrogen ions and you find the pH as the last thing that you are going to have to do. You've seen the kind of question that you expect in terms of complexity and the seriousness that you would have to put in as you're answering questions is quite demanding. The level of the questions that you expect would be up to somewhere there where we would expect that our students should be able to deal with these kind of questions. When they are able to answer these kind of questions, then, like I said earlier, we would be confident that we would have taught you and you would have learned some very nice and serious concepts. Okay. So, as an example, calculate a pH of 0.1 molar concentration of acetic acid. So here, again, that was a very good question that was asked. Someone was wondering, why would we refer to an acid? We're using the word basicity, monobasic, because we are dealing with acids. And I'm sure that has been clarified. And from this point onwards, we should be able to define what basicity is, and we should be able to deal with the concept of acids being monobasic, dibasic, tribasic, tetrabasic, whatever it is, or simply just basic or polyprotic kind of like concept of acids. So we did introduce you to some acids, some of which we are still able to remember in terms of their formulas, both in the acid base and salt topic, as well as in organic chemistry, which was the introductory organic chemistry that you did back in secondary school. Even here, we are going to introduce you to organic chemistry at a slightly higher level, of course, just building up onto the concepts that you did learn. And you are going to be introduced to a lot of acids, carboxylic acids. So we will not most of the times give you the formulas of some of these acids. So it will be up to you to actually, to either being able to simply just figure out what the formula is supposed to be, or remember what it is that you'll have been given in terms of the formulas of those acids. So you see that the formula for acetic acid is a very simple formula, but we may bring in other acids, such as lactic acid. The concentration of lactic acid was this and that. So you should be able to figure out what the formula for lactic acid is supposed to look like. Or we tell you octanoic acid was dissolved in water and its concentration was this. So you have to figure out what the formula for octanoic acid is supposed to be. So at this level, you are expected to read even on your own, and of course not only focus on the things that are presented to you in these lectures, although we encourage that where to begin from should be here before you try to expand on any of the concepts that we would have presented to you. So you begin from what will have been presented to you in terms of the lectures, will have been taught to you by reading in a wider way. Okay, so those acids will be introduced to you again, and some of them will be given to you as examples in your introductory organic chemistry at this level once again. That is okay. So you write the dissociation equation for your acid, then you use the ICE table to figure out what the concentrations are going to be at equilibrium. So you have your acetic acid, you have your hydrogen ions there, and you have the acetate ions. So when these, before the dissociation of this particular acid, acetic acid, we did not have any hydrogen ions in solution, and neither did we have any acetate ions in solution. So these would have to come about only after the acetic acid itself will have undergone dissociation. So that is why we see that the initial concentrations, this is zero, that is zero. That is if there is any of us that might have missed these concepts when we were looking at them in the previous topic, which is chemical equilibrium. For most of us, this is walkover. It's something that we are able to understand very well because of the way we had executed the previous topic. Kudos to us. Yeah. So in terms of the changes, this is a very straightforward kind of reaction. It's going to have to move forwards. So you expect that there is going to be a decrease in the concentration of acid and an increase in the concentration of the hydrogen ions and the acetate ions, whose concentrations were initially zero. Yeah. So the changes are going to be 0.1 minus x and plus x and plus x in these, or rather x and x in terms of the concentrations of these other species that are participating in this particular established equilibrium concentrations in terms of x, and you throw them into, you would have to throw them into, let me just erase this. You throw them into the law of mass action for the dissociation equation for acetic acid. So using the law of mass action in terms of Ka, you substitute there for those concentrations with X and X this side. Then the denominator, which is the concentration for acetic acid at equilibrium, you substitute with that. But then, because the value of the Ka is small or, that is what you are going to assume as it being small. But of course, you would have to test your assumption at a later stage. You are going to assume that the concentration, the change that would come as a result of the differences that will take place when this one undergoes ionization would not be very significant. So you assume the initial concentration, the denominator to simply be equal to the initial concentration, which is going to be 0.1. Then you compute for X. The value of X found here, because the dissociation equation is showing us coefficients of 1 to 1 to 1, the value of X is going to be assumed to be equal to the value of the concentration of hydrogen ions. So once you find the concentration of hydrogen ions, then you find the pH. This is what this is the part that I referred to when I was warning you earlier on, where I said I would have to put all the concepts that we have acquired together. I mean, that have been acquired thus far. We put them together. We amalgamate all the concepts and come up with a solidified question with all concepts involved. You take all the steps that are needed. If it means you determine the direction of the state of chemical equilibrium using the reaction quotient value, you would have to do that. So everything would be put together, then we come up with a question that is of examination standard. And only those of us that would have taken the warning seriously, or the advice seriously, and have understood all the concepts. If you face any challenges along the way, I'm one person that does not chase students when they come to my office to ask questions. I will allow you to ask your question, and I will attend to whatever issue that you might have in terms of you not having understood any given concept in these topics that we are presenting to you. Understanding some of the concepts. I taught stoichiometry and demo concept, the first topic that you did after the introductory part of this particular course. I taught some groups from CHE 1010, and there were a number of your friends that had difficulties understanding some of the concepts. They kept coming, and I explained things to them, and they understood. I taught them atomic structure, I taught them periodicity, I taught them chemical bonding. They had challenges in terms of understanding some of the concepts. They still kept on knocking on my door, and I would allow them to come in, and I explained concepts to them. So if you face challenges, the strategy to use is not to allow things to ferment. You do not understood. You've not understood something, then you allow the problems to just keep on, worsening. Then when it is too late, that's when you try to seek help from people. They will not help you, because at the time when you might need their help, they are going to be very busy also. You might want to run to your friends who are also trying to prepare for their exams. So the time to deal with the issues that you might have is now. Okay. So you use the value that you'll have found, then you find your pH, and that is the way these questions are supposed to be dealt with. So in the remaining 5 minutes before 10 hours, let me just quickly explain one last concept. Then we can call it a day once we are able to do that. So let me just quickly, I was trying to admit one of our friends into the session, the learning session, who was just joining us. Okay, so when you have bases, weak bases, you would have to use almost the same approach that we have just used. For those of us that are able to remember what we had said earlier, to say there's an easier way of determining the hydroxide ion concentration, or even the hydrogen ion concentrations whenever you're dealing with weak acids and bases. You would simply have to use this formula here. So if you had pyridine, which is a concentration for pyridine is given as 0.050, and the Kb value has been given. So you can either use the ICE table method, or you use the formula method, depending on which one you are able to remember faster. If you do not remember the formula, it doesn't mean you're doomed. You can use the ICE table method, or anyone else who may not be able to but of course, I would encourage all of you to practice the method where you're going to have to use the ICE table, because it's not every time that you may have to deal with questions where you might need to use the formula. So in this case, you use the formula itself to find the concentration of hydroxide ions. You multiply the Kb value and the concentration for the base, giving us the value of hydroxide ions as being equal to 9.22 times 10 to the power -6 molar concentration. So this then is thrown into the expression for POH. Be very careful here. You have been given a base. So the hydroxide ion concentration should not be thrown in the expression for pH is equal to the negative log of hydrogen ion concentrations. You just assume that whatever happens, things would work out in the end. No, it doesn't have to be that way. Remember what I just told you. Chemists do things correctly. So you find the POH by taking the negative logarithm of hydroxide ion concentration. You find the value of POH. Then using the value of POH, you remember the relationship between pKw and pH and POH, where the pKw value is 14.00 is equal to pH plus POH. So the difference between 14 and 5.0 is equal to 9, which is characteristic of the pH of a weak base, such as pyridine. If you're able to remember the formula, well and good. In case you're not able to remember the formula, you can still answer the question by writing the dissociation equation. You write the dissociation equation for pyridine. Remember that pyridine, being a molecule with a lone pair of electrons on nitrogen, it can abstract hydrogen from water molecules and become protonated, in which it results into formation of what you might refer to as a conjugate acid. So you've got the conjugate acid here and the conjugate base here. Then the expression is written without the water molecule, because the contribution from water molecules is regarded as being insignificant. So we don't include water molecules in these expressions. Then we use the ICE, using the ICE table. So using the ICE table, we see that the concentration for the pyridine molecules and the protonated pyridine molecules there and the hydroxide ions, the initial concentrations are 0.050 there before this one dissociates. We don't have anything in terms of that, and neither do we have anything in terms of that. So those are regarded as being equal to 0 and 0. Then the changes. The pyridine concentration would decrease, while the protonated pyridine molecules, the concentration would increase, and you have the concentration of hydroxide ions also increasing. Then at equilibrium, we are going to indicate the concentrations in terms of X. So it's 0.05 minus X and X here. Then using the law of mass action, which we have just indicated here in terms of Kb, we can throw in those equilibrium concentrations. Okay, and then we would have this expression. So where those concentrations are supposed to be, we put X and X. Then down here we put 0.05 minus X as its concentration, assuming that the value of Kb is small enough. Then we are going to ignore this part here. We simply substitute with the initial concentration that, or we approximate, in other words, and substitute it with that. Then when we find the value of X, which is what we found in the previous slide there, we say the protonated pyridine molecules and the hydroxide ions, the concentrations are equal to the same concentration as that of the value of X, because the coefficients are 1-to-1 throughout in the dissociation equation. Then we find the value of POH using the concentration of hydroxide ions, and then the difference between 14 and 5.0 is going to give us the pH value for this particular weak acid. Okay, so for this group, we have done quite a lot in this particular topic. So all that we need is one more session for us to be able to finish the topic itself. So work together with your group representative to try and find time to for us to meet again, then we can finish the part that is remaining in one session. Oh, thank you so much. Thank you, my friend. I'm humbled to hear that. Yeah. So you find time to make sure that we meet again, you guys, so that we finish the remaining part of this particular topic. I want to make sure that when okay, so the let me just try to see if I can read the what is the message that has just been sent. Yeah. So make sure that you find. Yes, sir, could you please add another example in the next session? Okay, sure. We will add another example. Don't worry, I'll put another example so that we are able to understand these concepts fully. That's very good. Okay. Make sure that you find time again. We meet and finish off this particular topic. I want you guys to be able to enjoy the questions that you're going to find in the test once you come back to campus, and also in the exam. Thank you so much for finding time to join in this particular learning session. I will surely see you next time. Yes, the notes are going to be shared. Don't worry. The notes will be shared, you guys. Don't. Yeah, the notes will be shared. Okay. Good day. Good day. Good day.